Welcome back. We're going to talk about linear regression today. So we've been talking about analysis of variance, and so the homework that was due will come back on Wednesday. The next homework will be posted pretty soon and be due the Wednesday after, because we're going to spend a couple days talking about linear regression, how that model works, what we do with the estimates in terms of inference, predictions, and then Friday to Monday is an Easter break. So we'll have it do that Wednesday. Things are broken up so there's not a great density of homework relative to the number of days in the week. I mean, there's a couple days off, so you might be doing other things related to Easter travel or something. But there's the project that's there, so you can think about a data set, think about some things that you want to do. If you want a data set in a particular area or are thinking about things and want to just email me with some initial ideas or thoughts, I'd like to do something on this but not sure where to get started, or look in the book or online a little bit more and say, I found this looks like something maybe I could do. I'd be glad to kind of have a back and forth and to try to flesh out a few ideas and make it a little more specific. Because in this, you don't need to do a million things. It doesn't have to be an enormous project, but you want to do something specific and focused so you can write about it in some detail. So we're going to look at linear regression and correlation today. So the scenario here is we have some data, pairs, x1, y1, x2, y2, on n observations, x in, y in. Both are quantitative measurements on something, and if we plot them on an axis with x and y here, each of these points ends up being one point on that scatter plot. And so we can have different points along here, right? And maybe it's going something like that. And so the basic question is, are these variables associated? Are x and y associated with one another? And if there's many possible patterns that you could be looking at, they could be going up together, they could be going down together, they could be tight around a trend line or more spread out. It doesn't have to be always one direction. It can be going up for a while and then turn back down. And so there are many different patterns. Generally we note in describing these, are they, we look for kind of a positive versus negative association. Tend to go up together, tend to go down together, or is it something more complex? And then kind of the strength. We will have some numerical measures like correlation of this, but what is strong or weak sometimes depends on the field of study. In physical sciences, where you apply a certain force and you get a certain reaction, it can be quite strong. In social sciences, psychology, economics, the relationships between factors, quantitative variables, can be much less strong, but still a significant relationship that might be worth looking at. Right? And so in linear regression, we are looking for a straight line that's going to predict y from x. So in linear regression, we think about y is an outcome or a response. And x is thought of as a predictor variable or explanatory. Different words are used. Sometimes y is called a dependent variable because it depends on values of x, and x is more called independent variable. Different terminologies, right? And in some settings, you're in an experimental setting. Like you can actually set the values of x. You can adjust the inputs of the amount of chemical or amount of product that goes in, or amount of force or velocity. So you can change x. Then x is more, in this case, is explanatory or independent. And then y changes with that. In many cases, though, there's not necessarily so much of a cause-effect relationship. They're just kind of going together. One might be influencing the other. You're more just doing prediction of that without as much of a cause. Right? And so in linear regression, we're going to put a line, a straight line between these points. Yeah, something like this. That's generally increasing, generally kind of strong. But we want to find some line here that describes that increasing pattern well. Right? Once you have a line, you can give me any value of x and tell me what's the predicted value on that line, and that maps over here to some y value. And so you can get predictions from that line. You can describe how close the line goes to all these points, so you can get some errors of things in there. But the question is which line do we want to use? So the line is going to have, generally has a an equation something like this, right? The intercept and the slope. So here A is the intercept, and B is the slope. So as x goes 1 unit, right? As x goes 1 unit, then the y value changes by b. And if b is positive, it's going up as x is going up. And if it's negative, it's going down as x is going down. And so the question of which one do we want to do? Right? And so the principle of these squares says to look at these deviations, right, about the line, these errors. These are either called errors or residuals. And choose a value of a and b, an intercept and slope, to minimize the sum of those squared errors. That's the principle that's used with regression. You could do a number of things. You could figure out a line to kind of eyeball it, make it look good. You could maybe take absolute value of those residuals and move the line about to try to do it. The particular one for all these squares is where we could choose A and B to minimize the sum of squared residuals. And the sum of squared residuals, if we put a little hat on y to denote the value of y on the line. So if x of I is the ith point, this is either called the fitted or also called the predicted value of y when x is a particular value. We're going to look at the difference of the actual yi minus its predicted value. Some of those are positive, some of them are negative. We're going to square them all, so they're all positive, and we're going to add them all up. So that's called the sum of squared residuals. And if we choose a different value of A, a different value of B, it's going to change that sum, right? You can, if you raise a line, it'll go closer to some, farther away from others. If you tilt it, right, you can change those two things into different lines. And there's one line that minimizes that. The solution of to this is called the least squares of y. And there's an explicit equation for it. It's actually a calculus problem, taking derivatives with respect to these two parameters, this a and b, the intercept and slope, and setting two equations equal to 0 and solving it. The equation for b is the sum of xi minus x bar times yi minus y bar is in the numerator, and the sum of the xi minus x bar squared is in the denominator. Once you calculate that slope, the value of a, the intercept, is related to that, the intercept, or the y average, minus b times the x average. So if you give me the data points x and y, I can go through and calculate the averages. I can calculate the deviations of the x's and the deviations of the y's, multiply them together, and produce these two numbers. And that's going to give me the solution to that problem. Right? Okay. Yes.
So that just gives you a formula for the line where length is closest to all possible dots.
Yeah, so it's close to the dots in the sense that if you put down the line and calculate these distances, you can kind of view those as springs kind of pulling on the line, where the strength of pulling is kind of the square of that distance. So a big residual right up here really is kind of trying to pull it up a lot more than one that would fall near the middle of that line, right? So that's the solution that would minimize that sum of squares. If you move it higher, it will balance out to be not as good, that solution. So let's look at one brief example, and then we can talk about inference for these things, what's going on with this. Right? So in R, does everybody have a copy of this here? So one data set that we can use for this is about Old Faithful geyser in Yellowstone National Park. So has anybody been there and seen Yellowstone or Old Faithful? So it's kind of neat. There's geysers all over the park and hot springs that have bacteria growing in them that create colorful patterns and things. It's kind of a neat place to go camping and so on. But the Old Faithful is kind of on a very regular pattern, every hour and a half or so, erupts, right? And it shoots hundreds of feet in the air and lasts for several minutes. It's hundreds or thousands of gallons of water is shooting up in the air. It's super heated. But in the lodge is a sign that says the next eruption should happen between, within 80 minutes to 90 minutes from now. So you can walk around the grounds, look at other stuff, get a hot chocolate or something, and still get back in time to see that. You don't have to sit there for an hour or 2 hours waiting for this thing to happen. And I don't know exactly how they do it. It's probably a little more sophisticated, but there's a data set here called Faithful that's included with R. And in it, it has eruption time, how long the eruption goes for in minutes, and then the waiting time in minutes till the next eruption. So an eruption starts, it starts to shoot up. It erupts for 3.6 minutes, and then 79 minutes later, there's another eruption. Right? So somebody wants this over time. And so these are all the XY data, the eruptions and waiting time. If you plot those, this is what it looks like. Right? Here's the eruption times, here's the waiting times, and what do you think how would you describe this relationship? Yeah, pretty good, strong. It's increasing, positive, kind of a tight cluster. There's a little bit more to the pattern than just that. Right? It's kind of these two clusters. There seems to be some big eruptions and some smaller eruptions, but kind of less in the middle. So maybe there's something going on there. Right? We will talk about correlation soon, but the correlation between these two variables is about 0.9. correlation at most is 1, so 0.9 for something like this is pretty strong. Right? In R, we can calculate the least squares regression with this command here is LM for linear model. Linear regression is an example of a linear model. So this is an LM. And then the waiting time, there's a little tilde there. And this is their syntax for saying that this is the y variable and that's the x variable. The waiting time is a function of eruptions, and it tells it what data set is. And summarizing gives it in a nice little format. Yeah.
Just going back real quick to the correlation, which one do you read first as you read that? Is it waiting, like, I don't know.
So so the correlation of eruptions with itself is just 1.
Right.
Right, so what it does is, so eruptions with waiting time or waiting time with eruptions, correlation isn't going to matter what order it goes in. Right, so the correlations of eruptions to waiting time is going to be 0.9 and same thing. So correlation is just a measure of strength of association.
Like those 2 different 0.9s, they couldn't be different values.
Right,
Okay.
right. Yeah, these would be the same values when it comes out in that.
Okay.
Matrix. You could tell it to do a correlation between eruptions and waiting, and it would just give you the 1 number for that. If you have several variables in there, it'll give you a two-way matrix that will give all the different pairs. But there's a correlation is symmetric and would be the same value for each, whichever order. So this one gives us an equation. This summary thing, right, gives us an equation. Gives us a bunch of stuff. It tells us what our function was that we called. It was this linear model function. It gives you a little bit about the residuals, right? So the residuals are the vertical distance, so the errors. So smallest error is about 12 minutes off because the vertical distance is waiting times. Maximum difference about 16 errors. So just a little summary to give you a little picture of what those look like. And it gives you this equation here, right? That gives us some coefficients. So it's intercept and eruptions. The x variable is eruption, so it's giving us the multiplier of that, and a couple other things that are there. So what comes out of that output is that for these old faithful data, so the coefficients there of our line, the intercept in here is 33.47, and then the next coefficient is 10.73, rounding a little bit, times x, and the x value is eruptions there. So this is the minutes, I call it, the minutes of eruption of this geyser. And then the y is the predicted waiting time. Y is waiting time, so this y hat is the predicted waiting time. And so as the eruption value gets bigger, as it goes for a long time, you have to wait a little bit longer. So if eruption is 2 minutes, right, then we're going to get a predicted waiting time of 33.47 plus 10.73 times 2 goes in there, so 33.47 plus 21.46, and so 893, and so 4 and 5. So about almost 55 minutes it would be your prediction for the waiting time. That's it. And that's the least squares fit. Seems very appropriate in this case. There's not many big outliers, not much of a strange pattern, deviation from any part of the space. It looks like that's what it really looks like, right? But our output here gives us a number of other things. So underlying this is a model. It's a linear model. But any questions so far about? So 2 minutes, right, would be about here, and so we produced about 50, so kind of in the middle. The line would go in this middle of these plots. We can add that line to the plots there, so you plot it. This AB line, slope-intercept form line, can take the output from the regression and put a line in there, and that's our predicted value. Right? In fact, for every value of x in our data set, we can get the predicted value. Right? Fitted is it will create the fitted values, the predicted values, the y hats from every single one. So this thing will give all of those, and we can put the points on there as little x's. Right? So all the points are, it's kind of messy, right? But for each one of these, like this little circle here, based on that x value, its prediction is on the line. Right? And the distance from each of those points to, so some of these are big errors, but they're kind of balanced by the ones below and so on. Those are the predictions there. But there's also the standard error and p-values and so on, and significance. So we're estimating something, we're estimating some coefficients. We're estimating some parameters. So there is a statistical model underlying this. So our statistical model relates y to x. Alpha plus beta times x plus some error. So alpha and beta is our parameters. They have the same interpretation as the A and B. X is the values of the eruption times, y is the waiting times again, and there's an intercept and slope, these unknown parameters. So if we knew the true chemical, physical process going on and knew alpha and beta, we would know what the real relationship is. But we only have 272 data points in this case, and so we're estimating that. These epsilons are supposed to be IID. So IID is the standard acronym for independent and identically distributed and it's normal, the mean of 0, and some variance, some constant variance. That the points don't really fall on that line, but there's some random noise about the line, right? And so on average, you're on the line, because the average error is 0, but you're plus or minus a couple standard deviations, typically around that. And the shape of the error distribution is roughly normal. Right? So if the real truth is here, as alpha plus beta x is this line, and so we take some value of x we're interested in, we would expect the y value to be on that line. That's really the model. That's the true probability model underneath there. But they're going to be kind of plus or minus some amount. Right? And it's plus a couple standard deviations, minus a couple standard deviations, about the line is typical. If I could make this in 3D, right, and make this thing kind of stick out here, the probability distribution that would kind of describe those would be little bell shapes, giving a sideways bell shape curve. Right? Now the density of those on this vertical line would kind of look like that, right? That if you had a bunch of points at the same x, you would get a bunch of points that are kind of close here and a few that are a little further away. And just kind of the concentration around the line would kind of look like a normal. Like if you took the residuals would look like a normal around that line. And this kind of slides up and down this whole thing, very much like these data. This is an example that seems to fit this model reasonably well. Right. And that would be the error structure that's on. So we want to know the intercept and slope. And so we can make a confidence interval, let's say 95%. Confidence interval for the slope, beta, is calculated as the estimated slope, so this is the estimated one. And it's going to have a t-distribution. The t-distribution involved here. The upper 97.5 percentile with n minus 2 degrees of freedom, and then a standard error of this. So we're going to do b plus or minus a t-value times its standard error. The formula for the standard error is going to be an s calculated on the residuals divided by the square root of something related to the spread of the x's. This s is an estimate of that variance of the residuals at sigma squared. And the formula for it is 1 over n minus 2 the EI squared, where EI is the error, the kind of realized error, 1 over n minus 2, I going from 1 to n of yi minus yi hat squared. So without going into, yes?
For the standard error, why would it not be the n, the number? Why does it relate to the residuals? For the
Well, why does this one relate to? Well, so there's two parts going on, right? So in the model, there's these sigma squared is a variance of residuals, right? And so if we take the actual errors, right, we want to take something like a sample variance of those related to those residuals to estimate that sigma squared. We end up dividing by minus 2 because we've estimated both an intercept and a slope. We've estimated two things. So it turns out in probability theory, the unbiased estimate of sigma squared has n minus 2 in there. For a big sample size, it's not going to make a huge amount of difference.
And then for the
So the standard error of B, right, why do we have this then? Well, it works out algebraically that that's what it is. But what does that end up telling you? So when do you know a slope really well? If you have a bunch of points and they're all at the same x, you might know the response at that point pretty well, but how's it changing? If the x's are spread out, right, you see that change over a long period of distance. And so the more spread out the x's are, the greater is your ability to discern what is the average, typical change. And so the more spread out the x's are, the more of them there are, because this is going from 1 to n. This is kind of replaces just that algebraically. That ends up what it ends up being. The more spread out the x's are, the better you can determine that change. If you only had observations in a very narrow range, it's hard to look at change. So anyway, that's what ends up being. And our normality in probability theory is why we end up using a t-distribution. It would be normal if we knew sigma, but we're estimating it, so it ends up being t for much the same reason. This one, degrees of freedom, we've seen degrees of freedom change like in a ANOVA for different purposes, right? And in this case, we're estimating two things to get our residuals. Right? We're estimating the intercept and slope, so it ends up being n minus 2. So, mostly we're going to use, that's the kind of explanation of what is there in this output here is it gives you a standard error. It gives a standard error for the intercept. In some applications, you're interested in the intercept, but in many, it's most primarily the slope, the rate of change. And we're going to focus on that one. So this gives us a rate of change here. I mean, an estimate of 10.73, a standard error of 0.31. There are 270 degrees of freedom. It mentions it a couple times here. There was 272. So the 0.975 quantile for a t distribution with 270 is 1.97, just about, not much different from a normal. So our confidence interval is going to be 10.73 minus that 1.97 times the standard error. This standard error here is already incorporating S and the square root of the sum of squared x deviations, right? That thing up to, right? So we get a 95% confidence interval for the slope that goes from about 10.1 up to about 11.4. So in the Old Faithful, our 95% confidence interval for beta slope, 10.1 up to 11.4. Now the units on slope are kind of interesting. 10.11, 11.35, let's do that. What are the units on slope? Bless you. So the equation, right, we have y hat is a equals to x. X is in minutes of eruption. And this one's also in minutes.
So
And
that's the rate of change.
it's a rate of change, right? So it's, how many minutes is it going to be? This is waiting, and this is eruption. So they're both in minutes, so it looks like they cancel, but they really don't. Right? So one is in minutes of it, this is minutes of waiting per minute of eruption. We'll do a different example that's not quite like that, right? So. So we're 95% confident that the actual rate of trade-off is somewhere between 10 and 11 minutes roughly. So sometimes you report a confidence interval for the slope. You can also test if the slope is 0 or not. Right? You can do hypothesis tests about the slope. So hypothesis tests. So there's a null hypothesis about the slope. Say that it's some beta 0 value. You would get this from previous studies or scientific hypotheses based on it's a physical system and looking at reactions and things, a certain rate that you would expect, right? Versus an alternative that's not equal to that. We can test this hypothesis by forming a t-statistic that is the estimate minus the null value. So this is estimated slope. The beta 0 is the hypothesized value about the true slope divided by the standard error for b. And so it's b minus beta 0. And then there's a standard S to B, and then the thing that's like sample size but special for regression. That's down there. Very often, beta 0 is set to 0. Right? Because if beta 0 equals 0, beta equals 0. What does that say about our model? No correlation. Y is not changing on average with X, it would just say that Y sub I is alpha plus some error. No X's at all. And so a graph of Y versus X, we would expect them to be flat. And the points would just be random scattered, up and down around this without any trend up or any trend down. The null hypothesis if beta is 0 is just flat, no slope. So in this case, the estimate that comes out of there, the estimated slope is 10.773. The standard error was 0.31. And so this t-value is 34.09. There's like no question that there's a relationship. We were tending to compare that to degrees of freedom with 270, the 975.4, that t distribution was about 1.97, and our t statistic is enormous compared to that. From the plot, right, the chance that you would get this strong of a pattern, if there really were no relationship, is basically 0. Just not going to have that ever happen. So we reject. And conclude that it's a positive slope because our estimate is positive, and our confidence interval, right, has told us that as well. Our confidence interval was our confidence interval is, it's more like 10 to 11. It's not near 0 at all. So that's part of linear regression. The other thing you can look at is this S sub E. This is, what is it called? On the R output, there is a line on there called residual standard error. It's kind of a standard deviation, really. Right? It's the square root of this standard deviation of the residuals. For the Old Faithful case, it's 5.914. And that is what we use to estimate that variance, right, in that regression. So how does that play out? Where does that show up? How can we visualize something like that? Right? So in our output up here, there are these residuals. So sometimes it's, instead of repeating this whole command here for doing the whole linear thing, you can save the output of that model computation into an object. So this line is going to save the resulting of fitting that model to something just called mod. So what is mod? Just type mod. It gives a little bit of that information there. Mod really is a list and has ways of displaying itself. So if you summarize that, you get all of our output we had before. The residuals are the errors for all the points. Some are positive, some are negative, so it's actually looking at all those differences. If you do a histogram of those residuals, right, that's what the empirical errors look like, right, the residuals, the differences. Centered around 0, some positive, some negative. If I put a line at 0, right, that's the 0, 1. And then that sigma value, it's really the estimate of sigma, but our computer code is just calling it sigma to hold on to it there. That value is this 5.914. It computes it as part of things. If you take the sum of the residuals of the model thing and then square those, right, and divide all that by the 270, right? It's 272 minus 2. Right? There's that value. The square root of all of that thing, right, is this error value. And so this is a normal distribution. So the normal distribution, most of the values are within about plus or minus 2. Right? So I'm going to put a bar at plus or minus 1 sigma, plus or minus 2 sigma, and that's kind of what it looks like. Right? Plus or minus 2. There's a few outside, 272 observations. You know, you get a few that are out in the 5% tails, 2.5% tails. If you go back to the whole plot of the original data with the line on it, right? The plus or minus 5, plus or minus 10 is in this vertical direction. Right? So roughly, if you wanted to predict where this is going to be, right, you could take a prediction, how long you would have to wait. When should you be back to see the next eruption? Well, if you do the prediction and then kind of subtract about 10 minutes, you're pretty safe. Right? Maybe you want to be 12 minutes, 13 minutes, 15 minutes, you probably wouldn't miss it. If you come right at 10 minutes, yeah, there's a couple times out of these 272 times, over the week that you're going to miss a little bit. So if they said the next eruption should start kind of at the lower part of this line, based on that, most people would be there pretty accurately, right, to see it. The data also are supposed to be normal, right? So we could do, the histogram looked roughly normal, a little bit different, but not too bad. This Q-norm plot gave us a straight line. That's straight, and they should be roughly normal. So it's, there's a couple times it's a little bit different from that. So that's part. So these t values, these are the p values. The probability that a t is greater than 34 is almost 0. Right? So in scientific notation, that's basically 0. There's a couple other things that are on here, this r squared and this, and there's an analysis of variance testing procedure related to this. So the other things that come out of that, I realize that some of this is kind of going through fast. You can spend a whole course talking about linear regression. Next fall, we have a course 451. 451 and 351 alternate years, and it's next year. The fall is 451, and part of that course is a couple weeks on linear regression methods. So there's an analysis of variance table for regression. That often is to look at as well. So, kind of the total variability of y is often measured by how is the y values relative to the average y. How spread out are those? Right? But this deviation really can be decomposed into 2 parts, just like a notebook got composed into 2 parts. One is a residual. That's the residual we had we're trying to make small. Right? That goes into our sum of squared errors. And if you put y hat here, it's this other part. It turns out that if you square these, right, and then add it up over all the cases, that you get this first part. And you get this second part. And then there is a cross product term that goes to 0, that it cancels. It's kind of an artifact of that we're using slope-intercept form, and we're doing these squares. And it works out algebraically. So this is the sum of squares total. This is the sum of squares error. and this is called the sum of squares due to regression. Some software will call this a sum of squares residual. Usually a textbook tries to make a distinction between that there's kind of theory errors that come from the kind of underlying probability model, and then there's the ones that you actually calculate as distances from your points to your line. This says residual. Sum of squares regression is sometimes called sum of squares due to the model. And in some software packages like R, we'll put the variable, the x variable name there as the, so maybe I'll call it sum of squares x. We could call it different things. So the sum of squares total gets decomposed into this error, which we hope to make small, and this one to model, which we hope to make big. So if the y's are all close to the y hats, that's the y hat I. If those errors are small, that'll be good, and you'll get a small sum of squares error. If the model is changing in a steep way, so that the y hats are changing very fast with x, right, then this will be big. If the model is almost flat, and there's not much difference in y, average y, predicted y as x changes, it's flat, right, then it'll be small. So a picture here versus, so this is y bar, this is y bar, and this is the y hat line. In this case, the sum of squares regression is big. In this case, the sum of squares regression is small. So it's a trade-off between these two things, right? If you want a steep slope, either going up or down, so that x makes a big difference in y, you get a big sum of squares regression. And if the points then are spread really tightly around that, this is small, but they could also be kind of diffuse. Right? So a measure of how well you do in regression. How well does one variable predict another is this thing called R squared. It's either a sum of squares regression over sum of squares total, or it might be computed as 1 minus the sum of squares error over sum of squares total. It's between 0 and 1. And if it's 1, it's going to mean that you're perfectly on the line. No deviation. All the points are exactly on the line. R squared of 0 is going to be just complete random scatter. For Old Faithful, the output gives us a value, where was that? Oops. I think point, let's see. I'll just pull it. So this one, it's called multiple R squared here, is 0.81. So more than halfway to the maximum. Old Faithful. R squared is 0.81. I guess interpreted that 81% of the variability in Y, 81% of the variability in the waiting time till the next eruption is related to or explained by the previous eruption time. And so it's 81% of Y explained by X. You know, it's kind of speaking loosely because not necessarily exactly causation in all contexts. And it's really just through that linear model. There could be other ways, if it's a nonlinear model, then there could be a very strong relationship, but it's not going to be perfectly straight. So it's kind of the higher the better, up to 100%. And the other thing you see then is the sum of squares get put into a table. So, for this, there's a regression, and there's a error total. The sum of squares is the sum of squares for regression. Sum of squares error, and then sum of squares total. There's degrees of freedom associated with these things. With regression, there's only, in this case, there's only one. We just have one predictor variable, so we just get one there. If we were going to describe the data, we could just describe it with the mean. But instead of doing the mean, we're going to do a slope and intercept. So we're going to have one more parameter. Error, n minus 2, because again, we have the slope and intercept. We have two parameters that are needed to describe that model. Mean squares are formed just like the mean square regression. The sum of squares regression over 1 in this case. The mean square error is the sum of squares error over its degrees of freedom. And an F statistic is formed, which is the mean square regression over the mean square error. So this gets used, that's just another implementation, another way of testing. Is there a significant effect of the X variable? The X variable in the model. It basically, in this form of regression, when there's just one predictor, is doing the same thing as the t-test. So if we have a null hypothesis that says that the slope is 0, no association, versus an alternative that theta is not equal to 0, we're going to reject null hypothesis if our F statistic is greater than a cutoff of an F distribution. Well, the upper kind of 95th percentile of that F. And the F is a ratio. There's a numerator, degree of freedom, and a denominator, degree of freedom. And so that's what it ends up being in this case. So that F distribution is like this. And if we're out, if our F statistic is bigger than a cutoff value, that's going to mean that the mean square regression is bigger than the mean square error. The mean square regression is 3 or 4 or 5 times bigger than that. When is the mean square regression big? Mean square regression is big if the sum of squares regression is big. Right, so if there is a slope, if there is a steep slope one way or the other, relative to the error. So you gotta look at both. How close are the points to the line and how steep is the line? And this brings it both together. This one's really doing the same test as the t-test for just a slope. There are other uses of F, and usually when people present regression, they present both that. On Wednesday, we'll look at other uses of this F test for other things, like testing for regions or other different effects. in this application, it's implemented. If you give this linear model command here, right, and just do ANOVA of that, it figures out that you're doing a linear regression and gives you that ANOVA test. Right. I had saved that thing as mod, right, the model, and so it will do this. Right. So it says response variable is waiting time. We had 272. So instead of calling it regression, it puts the eruption variable name there. That's the x variable. So that's the systematic part, changing with x. Sums of squares for these two. Now, if you take the sum of the, I'm going to attach faithful, so I can just refer to the, if I take the waiting time as my x variable, minus the mean of the waiting time, right, and then square all those deviations. That's my sum of squares total, right? That's the 50644 plus 9433, approximately 9443. If I get the right, so that's approximately what that. These two things are the total. The mean squares doesn't change for eruptions. The mean squares error does become quite small. At 35 is about our sigma value. It turns out that that mean square error, just to see another relationship here, this mean square error that's there is the square of the residual standard deviation. And that would be what's generally used as this estimate here to the sum of the, what we can do, EI squared to the sum of the YI's minus the residuals squared. So some information gets displayed multiple times there. But in this, then the F value is 1100, which is enormously large. Right? The quantile we'd be concerned with for testing whether it's 0 or not is an F command. Quantiles for an F, 95th percentile when there's 1 and 270 degrees of freedom is 3.88. And we're at 1100. Completely off, but that's not surprising. We saw a very strong pattern. So in one kind of quick overview, that's a lot of the essentials that go into kind of the beginning regression. We'll have the homework that will be posted, that'll be due a week from Wednesday, will be very practical. We're going to look at one more example. Well, I guess we have time. Maybe we don't have too much time to, we can at least start looking at one. There's this one of this data set on trees, right? As I hope to just put, these are girth, height, and volume of black cherry trees. So if you're trying to harvest black cherry trees and for lumber, right, you'd be concerned with volume, presumably. Right? This pairs command, if I can make it just a little bigger here, this pairs command gives you some scatter plots of the variables. And so part of this story is which of these two things, girth or height, would you want to use to predict volume? This pairs thing, looking at this row, has volume on the vertical axis. So if we look at this row down here, it's about predicting volume. And on this one, girth is the predictor, and this one, height is the predictor. Right? Which of these two looks like the better one for predicting? Girth looks quite good, right? these trees, I think, were harvested kind of in a height range. I mean, they're not gonna take the little tiny saplings. And maybe there's some restriction that they can't take the giant old ones or something. We'll talk about correlation to start out tomorrow, but the correlation with girth was 0.967, very, very high. If you just do a plot of girth versus volume, you get with the least squares line in there. That is the least squares line coming from this output here. In any case, the R squared for girth as a predictor was about 0.93, about 94%. And and here's the example predictions. If you do height, though, the R squared is about 0.36, not nearly as good. So we're kind of out of time, but maybe look through that, look at the predictions a little bit there. We might start out reviewing a little bit of that one, and look at a little more involved example.
Can you go back to the slide for a second?
Yeah.
And then back one. Thank you.
Yeah.
So that,
Oh, right, yeah.
I was thinking to get it to fit normally, I could compare it to like moon phase and then maybe take the ratio of how much it changed from one to the next, to how much the moon phase changed
Okay.
from one measurement to the next.
Yeah.
And I was thinking of that one changes and then the other one's changing and they keep changing. That might be normal, but I might experiment with that
Okay.
for the project and see if there's any way I can tweak it to get it to look normal. But I'm just wondering if it's okay to, if that's like the whole project or if that's.
Yeah, so you could think, what do you want to, you just kind of just drift over time. So, do you want to report averages, deviation, the confidence interval for the averages, the average difference at the beginning of a time and at the end of a time, so it's either kind of a change in there. So you could demonstrate different inference procedures and then try an kind of an exploratory idea. So it's possible to display it and try out a couple things along the way. If you need to add a caveat as well, we don't really think these data are normal or there's kind of a trend pattern going on. Hi there.
Hey, I just wanted to let you know I have someone X with X on it and some of the test corrections.
Oh, okay, good, good. I'll do
And
that.
then this one was for homework 8, so homework 9, so I wasn't sure if I should deduct reduce sensitivity or.
All right. Let's just leave it like that.
Okay, sounds good. I put it in the
Canvas.
it's just that, yeah. So I didn't deduct anything.
All right.
All
Thank
right.
you very much.
You're welcome.
Yeah.
Have a great one.
You too.
Thank you.
Yeah. Hey, good. Yeah. So, but it's going to be kind of a couple different
Yeah, so I
parts in
can,
there.
and then actually writing that up as a project, would I just kind of walk through what I did and analyze the.
Yeah, I try
results of that?
to kind of put it in different sections or different
Maybe
themes.
contextualize it and then have like, here's what happened when I was looking at the rates of change. Here's what happens if you just look at, how well it would fit just any sine curve, like, or like, because I was reading on line about how you would fit, say, a sine wave or a cosine, and it said you can use the least squared method. You just have to say have like a times sine of b x, and then you do the same thing, and you try and get it to do a least squares
Yeah.
based on that.
That
So
can be done.
I
Yeah.
can look at that.
Yeah, that'd be
too.
neat to see how that works out.
Yeah, and then another statistics question. So my senior SEM project, I mentioned, I think a while back, on